Let's take a look at some techniques for evaluating limits analytically. So make sure as you watch this video, your cell phone is put away and turned off and you have your full attention for the next few minutes. So this is section 2.3 in our textbook. A few properties for limits that I want you to be comfortable with and familiar with are given in your notes here to begin with. So the limit as x approaches c of b, where b is a constant function, is just going to be b, that function itself. So for example, if I said, what is the limit as x approaches 2 of the function 6? That would be the constant function y equals 6, the horizontal line through 6, and that limit would just be 6. Nothing to think about because it's always that number. It's always 6. The next property, the limit of just x, so that would be the linear function y equals x, as x approaches c would just be c. The last example, the limit of x to the n as x approaches c, that would just be c to the n, whatever that is. So if I have the limit of x to the third power, for example, as x approaches 2, that would just be 2 to the third. That's all that is. Limits can also be added and subtracted, multiplied and divided and raised by a power. Limits are really versatile. So we can break them up by addition, subtraction, multiplication, and division. We can raise them to a power like an exponent, or we can multiply them by a scalar. Scalar is a fancy word for a number. So we can use a constant multiple. We can pull that to the front of a limit, and it's the exact same thing. Let's do some examples. So number 1, it says to evaluate the limit of the function 4x squared plus 3 as x approaches 2. So these properties here tell us that I can break this up and I can write this, for example, as the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of just the constant function 3. And then 4 is what we mean by a scalar, so I can bring that scalar to the front and I can write that as 4 times the limit as x approaches 2 of the function x squared, so that's what remains, plus the limit as x approaches 2 of the function 3. And so then that would be 4 times the limit as x approaches 2 of x squared using this property right here. That would be 4 times 2 squared plus 3 is the constant function, so using this property here, that would just be 3. So we can simplify it and say 4 times 4 plus 3 gives me a limit of 19, and that's the value there. Now, you might notice we could have just taken that 2 and substituted it back in from the very beginning. We would have gotten the same answer, and that's perfectly acceptable. You don't have to break this up and write this using these properties every time, but there will be times where breaking up and using these limit properties that we've talked about in this little section here will be helpful. So I wanted to give you just a quick example of that. Example 2, the limit as x approaches 8 of the cube root of x. We use direct substitution here, and we can substitute 8 in place of the x. Because this is really, I want you to make this note here that this is really the same thing as x raised to the 1/3 power because, oh, I put an infinity symbol there. I meant to put an 8. This is really the same thing as x raised to the 1/3 power. Remember that property from algebra, when you have a radical, there's an implied 1 here, a 3 here, that becomes x to the 1/3 power. So using this property, we can substitute that 8 right in and say, what is 8 to the 1/3 property? You can also say, what is the cube root of 8? And that is just 2. So the limit there is 2. Notice that really what we did on these two examples is we used what we call direct substitution. We can plug in or substitute in the limit we're evaluating at, the x value rather, we're evaluating that limit, so long as it's what we call a well-behaved function. So both of these make a note that we use direct substitution and just substituted those numbers in. As long as the function is defined there, or what we mean by well-behaved there, we can still use direct substitution to evaluate the limits, and that's a valid answer, or valid method rather. So the trig functions, the 6 trig functions, are generally considered well-behaved functions so long as they're defined there, which is true for any function really. So let's look at this example. The limit as x approaches 0 of the tangent function. Can I use direct substitution? So the question is, if I substitute in 0 for x, do I get a value here? Well, the tangent of 0, you may recall from pre-calc, that's the sine of 0 divided by the cosine of 0, which is 0 divided by 1, which in fact is 0. So that's going to be the limit for this function. X times the cosine of x as x approaches pi. So if we use direct substitution here, we get pi times the cosine of pi, which will be pi times the cosine of pi, which is -1, and that gives me -pi. Again, we're defined at pi. This function is defined at pi, so we can use direct substitution. So anytime we can substitute in and it spits back a number at us, it's defined there, it's well behaved is what we'd say, direct substitution is just fine. Now what happens on the other hand if the function is not defined there and direct substitution does not work? Take a look at example 4. Notice that if we try to use direct substitution first here, we would have -3 squared plus -3 minus 6 divided by -3 plus 3. That gives me 9 minus 3 minus 6 over 0, which is 0 over 0. And you need to start remembering this rule. I mentioned it previously, but I want to mention it again. Anytime you get 0 over 0, that means there is a hole in the function at that location. Does that mean that the limit does not exist? Not necessarily. It depends on the function. A hole can have a limit as x approaches that number. So we're going to have to do a little bit of work analytically to figure this out. What can we do to simplify this function? Well, notice that the numerator here will factor. And so this, in fact, will break down as the limit as x approaches -3 of x. Let's see, this will be x plus 3 and minus 2. All over x plus 3. Make sure I've done my factoring correctly, but if you redistribute, FOIL this out, whatever you want to call it, it will give me what we started with. So notice now that those x plus 3's divide out, and I'm just left with the limit as x approaches -3 of x minus 2 is the function that remains. And this is the same. This graph, if we were to graph this, would look the same as the original function. It would both look exactly the same. They would agree everywhere except for at x equals -3, because we said there was a hole at x equals -3. So, but the limit is the same, and that's the point. The hole does not affect the limit. So now we're going to use direct substitution on what remains. So we're going to say -3 minus 2, and the limit here would be -5. Let's take a quick look at this in Desmos. So I've got the function graphed here in Desmos, and you can see that x equals -3 right here. Desmos tells me that the function is undefined right there at x equals -3, but hopefully you can see that the limit there does in fact exist. Let me see if I can draw this on Desmos here so we can see this. As x approaches -3 from both sides, so as x is in this little narrow window, the y values also approach a value or a narrow window here at -5. So the corresponding x value, we've got a corresponding y value that we approach of -5. And that's going to be the limit, even though there's a hole in the graph at x equals -3. We still have a limit that exists.